We would focus on the views expressed in your last two books,
Okay.
Quantum Physics and Theology,
Yeah.
and Science and Religion in Quest of Truth.
Right.
And I have to say, John, I have enjoyed them immensely.
Oh, that's very kind.
Found them mind-expanding, I think is the word. You suggested I also read Quantum Theory,
Yeah.
a very short introduction. That, I have to confess, I found downright mind-bending. So, can I start with some questions about quantum theory?
Of course, yes.
I had the impression there might be some significance in the fact that you called the book Quantum Theory and not Quantum Physics.
Well, theory is a key term. It simply means a general proposition that covers a wide range of phenomena. So it has a sort of explanatory power, which is persuasive that it's expressing something there. So the basis of quantum physics is quantum theory in that sense.
Right, I mean, I did notice that you say, though we know how to do the sums, we do not understand the theory as fully as we should. And later you said, to be frank, we don't have as tight an intellectual grasp of quantum theory as we would like to have. How empirical is quantum physics?
Well, it's very, I mean, the phenomena what we're trying to explain are carefully measured, wonderfully accurately measured, actually, and we know a certain property of electrons to an accuracy which represents the width of a human hair in relation to the distance between Los Angeles and New York. Well, that's pretty exact.
So this is classical measurement, really. We know the...
Well, we have the results. Physicists tend to talk about that as phenomenology. These are the interesting things that go on in the world. They have suggested patterns about them. How do they fit together? How are they consistent with each other? How can we actually use them to gain further understanding to go beyond where we started? That's when we're trying to find a theory. And in relation to quantum theory, we have a theory which we have two theories, which of course is the paradox of that. There's the deterministic theory due to David Bohm. There's an indeterministic theory, which is the mainstream one. It's traditionally associated with Niels Bohr. So there's one thing, and also we don't understand. The thing we don't understand very well is how different regimes fit together. We understand the inner workings of the fuzzy quantum world pretty well. But how does that relate to the world of every day? After all, electrons and all these particles behave in odd ways, but we're made out of these things. How does it happen, if everything is so fuzzy and indeterminate, how does it happen that we are, on the world around us, in fact, on a macroscopic scale, is orderly and reliable?
Yes.
That's a deep question, which we don't have a totally, fully adequate, satisfying answer.
No. But then, of course, it's obvious, even to a layman, that in many of these areas we don't need to know. We don't need to know that, or worry about the fact that the world is 9-dimensional, since we operate 9-dimensional.
Well, I don't believe it is, but I can't
because we can operate with 3 dimensions, presumably.
Well, yes, but that would be that. I mean, that is the difference between being able to do the sums and fully understanding it. And physicists don't want to say simply, look, we can figure out the numbers. They want to say, the reason it's working this wonderful way, and it does work so beautifully, accurately, is, and then give a basic understanding to it. We need a certain degree of intellectual comfort and satisfaction.
Yes, yes. I noticed in one place you were a bit critical of Karl Popper's logic of scientific discovery.
Well, yes, I'm pretty critical of it. First of all, it's falsification is a much trickier concept than Popper really conceded anyway in his original writings. You know, the famous example is all swans are white until you go south of Western Australia and then you see a black swan. But is it really a black swan? Is it a long-necked duck? And so you have interpretive problems.
Yes.
Which means
I hadn't thought of that, I must say.
Yeah.
Well, you see, I mean, this is what one wonders. How falsifiable is quantum physics? It's evidently verifiable.
Yes.
Mathematically.
Well, I think ultimately all physical theories, and in fact I think ultimately all human understandings of the nature of reality, have an element of commitment to a point of view which is not logically coercive.
Yes.
You can say, look, if you look at say, the quantum world in this sort of way, you'll find that pretty satisfying, not complete, but a pretty satisfying understanding how it fits together. But I'm not going to say to you you're absolutely stupid if you refuse to swallow everything that I tell you about.
No. Well, you explain that much of quantum theory is unpicturable.
Yes. Yes. I mean, just take the fundamental quantum effect that everybody knows about waves and particles. We can't picture something that sometimes like a little bullet, sometimes it's a flappy thing. We know how to express that mathematically, and we know how to work with that. We also know that if you do, that the two different sets of properties are to some extent mutually exclusive. If you ask a particle-like question about, you'll get a particle-like answer. But if you ask a wave-like question, look at something like interference effects, things of that nature, then of course you get a wave-like answer. So we know why there isn't an immediate direct contradiction. But the fact that sometimes it's one and sometimes it's the other, this sort of ambidexterity, is not, as I say, we can express it perfectly, in fact, through quantum field theory, but it's not intuitively comfortable.
No. Are you ever worried by the fact that these phenomena are verifiable mathematically, and yet we can't prove the consistency of axiomatized systems like mathematics?
Well, that's Gödel's theorem. Yes, yes. Well, that shows there was a limit to these things. Yes, I think, and I think that most people forget about Gödel's theorem most of the time. But yes, it warns us that there is a limit to the powers of ratiocination, if you like.
But do you think most mathematicians and physicists recognise this?
I think certainly most don't, because mathematicians more than physicists recognise it, but most mathematicians don't really worry about it. If you're looking for properties in number theory, trying to do something about the distribution of prime numbers or something like that, you're not going to worry about the fact that the completeness of the real number system is not demonstrable